Hi everybody, my name is Matteo Ripoli. I'm a first-year PhD student working in the EP2 group and in the framework of the Zarathustra project. My thesis is titled Stability Analysis of Magnetized Plasma Flows for Speed Propulsion and is being supervised by professors Mario Merino and Eduardo Ahedo. So in this, okay, I was holding it. Reverse. All right, so in this brief presentation, I will show you the motivations behind the study, its goals. I will show you what has been presented in the literature up until now, discuss some original contributions, and then future efforts, future extensions of this present work. So by now, you might imagine why stability analysis for E-cross-B devices such as all thrusters and helicons is relevant, and that's because instabilities and oscillatory phenomena is quite important in is one of the major contributors in non-classical cross-field electron transport, and this is quite relevant in the case of magnetic nozzles, as this can impact, for example, magnetic confinement. Magnetic nozzles are devices whose role is vital in the acceleration processes happening in electrodeless plasma thrusters. And there is quite a lack of understanding of in oscillatory phenomena, primarily drift waves happening in these devices and their impact on efficiency. So the goals of this study, as a very first step, is to characterize wave-like behaviors from a fluid point of view happening in relevant plasma configurations, and to identify suitable onset criterion for their eventual unstable growth. And all of this will be useful to get a deeper understanding into instability-driven transport phenomena of plasma properties, their main physical processes behind them, and this will improve predictive capability and self-consistency of both analytical and numerical simulations modeling of plasma flows. So, for the state of the art, I will focus on local linear stability analysis or small perturbation analysis as a first step of the research. And when dealing with drift waves, which are driven by gradients of equilibrium properties, we need to look at the dispersion relation as the one that I show here, whose left-hand side describes ion dynamics and the right-hand side electron dynamics, and can be seen as a modification of what is called the lower hybrid mode. In the literature, there is most of the focus is pointed towards propagation in the direction perpendicular to the magnetic field vector. And in the case of a collisionless inhomogeneous plasma, here I'm showing you a graphical criterion for determining instability. As you can see, based on dimensionless plasma parameters, as you can see in the color regions, we have they denote unstable behavior, while the white region denotes a stable one. Collisions in general, sorry, from what we've seen, destabilize the plasma, so they widen the instability regions. And as I said, there isn't much being said about parallel propagation and almost nothing in the combination of both parallel and perpendicular propagation. So my contribution up until now has been that of generalizing what I've shown you previously, the special relation shown in the slide before, by introducing parallel dynamics in this term, okay, briefly. And so, okay, now here what I'm showing you, the process is complex, but what I'm showing you here is what is a plot of the solution of this equation right now. Solid lines represent temporal oscillations of the waves, and the dashed lines represent growth rate, same color, same wave. So a first effort has been devoted in the case of collisionless plasma in understanding the effect of K-parallel on known instability regimes. From what we've seen up until now, K-parallel seems to push instabilities at higher wave numbers. So in the end, to have a stabilizing effect on the plasma. At the same time, it also introduces a new instability regime in a collisionless plasma, which is driven by presence of K-parallel, of course, but also by a strong diamagnetic current for electrons and a small E-cross-B velocity. Of course, collisions destabilize even further. We have not quantified yet their effect, but we expect them to destabilize the plasma. And there is a paper in the making on this topic right now. So future efforts will be centered around moving to more complex geometries, so moving to extend it to an axisymmetric, slowly divergent plasma flow, which will simulate a little bit better what is happening in a magnetic nozzle. comparing predicted unstable behaviors with simulations, and then developing a quasi-2D code for global stability analysis of magnetic nozzles and such. And that was it. Thank you for listening. If you have any question.